for me at least, in the sense that I will talk about things that I spend my current time with, and what do I think about these days. A couple of rules of the game. I wanted to talk about liquid crystal elastomers, so solid liquid crystals. We have had some of this during the program, not a lot. We have had some of this morning with this nice SMEC decay presentation. And the other rule I gave myself was to try and get, I mean, not really problems, but thoughts out of experiments. Okay, so I'm an engineer, by the way. Real. Okay, so and the scale is the one of continuum theories. So it will be continuum theories, continuum mechanics. So mechanics of deforming potatoes, right? So there is a reference configuration, omega. There is a map, y, that deforms this object into a deformed configuration. Maybe there is a point here, x, and it goes to, okay, let's do it like this. It goes to y of x equals x plus u of x, which will be the displacement. Okay? And what I will spend most of my time on is nematic elastomers, not smectic elastomers, because it's, if you want, the simplest or the most widely studied case. Okay, so what's going on here? What goes on is that the isotropic to nematic phase transformation does not occur in a liquid, but it occurs in a polymer network with cross links, so in a rubbery solid. Okay, so the consequence is that ordering interacts with elasticity. So ordering causes distortion of the polymer chains, as it vaguely suggested here, but the chains are cross-linked, so this moves the cross-links about, and so there is interaction between nematic order and elasticity. So this is the proof of this. You see a strip of a nematic elastomer that is being cycled between the high temperature, which is in the isotropic phase, and a low temperature in which the system is in the nematic phase. So when the number is small, you will see the object elongated. When the number is high, you'll see the object contracted. So what's happening is that the chain align. So here n is supposed to be the nematic director. In this picture, n is vertical. And so with the isotropic to nematic transition, the chains align, the nematic mesogens align along the vertical, the chains stretch along the vertical, and this is the stretch you see. Okay? And you see a very large stretch. Here it's on the order of 200, 300%. But if I had to discuss this theory, it would take all my time. So instead of doing the real thing, I will do, in some sense, the baby version. So it's the kinematically linear theory. So I will pretend that these deformations are small, and I will use as a measure of the deformation, not the gradient of that map, but the typical measure in linearized elasticity, which is the strain, which is the symmetric part of the displacement gradient. Okay, so here denoted in a number of ways. So E sub u is like an operator on u. Okay, instead of doing grad y for the displacement gradient, I do E of u for the linear strain. Okay, so let's see what else is on this slide. So how does the theory sees, I mean, how does the model I'm going to describe very briefly sees this picture here? So there's one important ingredient which is common to phase, so symmetry breaking phase transformations in solid. It's the spontaneous strain, called Bain strain in the martensitic literature. So it's how much the system deforms as a consequence, locally, as a consequence of the phase transformation. And so here we see it in some sense. So it becomes long in the direction in which the mesogens align. And I will do an incompressible theory. These are rubbers, so shear moduli are much smaller than the bulk moduli, so everything will be incompressible. And so also the spontaneous distortion from the isotropic case will be volume preserving. So once you have said that the system becomes long in the direction of alignment, and how much long, how long, essentially by symmetry and volume conservation you have said everything. Because there's one special direction, the direction of alignment, all the others are the same. And if it becomes long in one direction, it has to be short in the other two directions by quantities of preserved volume. In the linear theory, this means that the trace... Sorry?
If what's over there is positive, if not, it would be also fine.
Okay. Okay, I take your point. Very well. So this is a spontaneous volume preserving transformation, and it's described by something like this. A constant, and then something which has unit trace. So here you see the fact that plus or minus n has no real impact in this theory. In fact, this is a very close reminiscent of the Gen order tensor. Okay? It has most of the same properties. Very well. So a matrix, so for this specific example, n, the direction of alignment will be the vertical. So the elongation direction will be the 2-2 component of this matrix, and the other two are opposite in sign and 1/2 in magnitude, and this is this object in this special case. Okay, so I want to build in one slide a theory for this. So the effects that we want to encapsulate, and I will do only statics, and by statics I mean I will believe in energy minimization. So I will write down an energy, I will look at the minimizers, and I will be content with looking at this. The dynamics is a big issue, and it could be the subject of other 20 minutes, but I think I will do only statics today. So what do we want to embody in this theory to reproduce this experiment? The fact that n likes to be vertical. So here it's slanted, but every time I repeat this experiment, n will align along the vertical. So we want this. And we want that the deformation is as closely as possible, ideally exactly the spontaneous deformation. If you have this condition, you have that the system is able to accommodate the temperature change without storing elastic energy, right? So there will be no residual stresses in the engineering language, okay? Which is very good because you can cycle then this many, many times. There will be no build-up of energy, stresses, fatigue, blah, blah. So you have something very reproducible, okay? So how to build a model that behaves like that? It's very easy. So a positive constant that sets the energy scale, some kind of shear modulus. And then I have an integral. And I build a theory so that I can read off the minimizers by minimizing the integrand. So I have the sum of two positive non-negative terms. It's 2 squares. And it's absolute values of matrices. So it's the distance between two matrices. So yes, so I will... so let's look at this one first, because it's the easier one, and it's the one in which I will really talk about. So when is this 0? It's 0 when this equals that. So this is the strain in the material, E of u. And this is the preferred strain corresponding to the fact that the director is vertical. Okay? So what this is telling you is that there is exactly one state of the system that is of minimal energy, the one in which the strain is like this special one. Okay? So this is so this is exactly like that, except that there's an extra variable. So if you look at what are the state variables of this theory, there's two, in fact. One is the strain, and one is the director. And so the theory has two strains, has two variables, and the way I enforce simultaneously the fact that n is along the vertical and the strain is the special one is by the interaction between these two. So let me show you why. In order for this to be 0, you need that this be equal to that. Oops, I'm sorry. Okay. For this to be 0, you need that the strain be the spontaneous strain required by the nematic director. But if you want them both to be 0, you need, in addition, that the strain be the special strain corresponding to a special nematic director. These two conditions indirectly force you also that n must be n0. Okay? So I took a little long way to get the two effects. And the fact that there is a parameter beta here is because there's also an alpha model in which instead of having this convoluted root, there's an energy term that is the angle between n and n0. So we could have done another energy in which you have the same term here, and here something like b times something that is 0 if and only if n equals n0. The reason I do this is because it's interesting. It's a beta model, not the alpha, so it's another one. But also because this is exactly the small strain limit of a model proposed by Warner and Terentian. Semi-soft elasticity of nematic director. So the relationship between these two is maybe a subject of a talk, but I will proceed in this way. Okay? So I hope it's relatively clear. And now we can do two limit cases. One is the one I want to talk a little bit about today. So imagine that, that now the nematic director is not really free to move around. So this is the case of a nematic glass. So there is a special direction, and the director cannot deviate from the special direction. Okay, so the director is frozen in a special orientation, and in the literature, this is called a nematic glass. So this is like saying that this beta is very large, and that n cannot deviate from n0. So this term becomes small or negligible with respect to the relevance of this term, and we get a simplified theory for nematic glasses. Okay? Which is simpler because what it's saying is that the strain wants to be a special value, a special strain, which happens to be the spontaneous strain corresponding to the special nematic director n0, but this is it. Okay, so how do we minimize this? So this is the thing that comes from incompressibility. How do we minimize this? Well, by saying that we minimize the integrand to 0, and so we want this to be equal to that. There are very nice geometric interpretation about this formula, so it's really the distance between a special set. In this case, it's a point set, but the other case, the other limiting case, is the case in which this term this time is negligible. So maybe beta is 0. Okay? And this is again an interesting case. It's the case in which there is no restoring force driving n back to a special direction. So this is the case of an ideally soft elastomer, for which there is a lot of theory. Incidentally, all the stuff about relaxation, so all the stuff about creation of microstructures, in this theory would be here, in the sense that you have the freedom to drive down this energy by playing on n of x, and by maybe texturing n, so by forming microstructures of n, you can drive the energy to 0. Okay, okay, so this second part is the part mostly related to relaxation. I mean, how oscillations of n can renormalize the elastic energy. But I will not talk about this today because I want to talk about something that can be discussed with the simpler theory, this one, so for glasses. Okay, and what is the question I want to pose? I mean, a lot of people are working on this. I'm just giving you a way of asking a type of questions on which many people are working. So the question is the following. Is there a way to use the mechanism I'm talking about as a way of understanding shape formation, shape selection, inducing shape changes through a phase transforming material in which we are able to texture this n0? So we prescribe some special n0 so that the minimization of the elastic energy produces interesting shapes. Okay? So here is one example, one experimental example. So this is a nematic elastomer. The example comes from the lab of Kenji Urayama. So here is a liquid crystal that it's liquid before being cross-linked, and it's placed between two plates in which the anchoring conditions are different. In one of the plates establishes a planar anchoring and the other one a homeotropic anchoring. And so when the material is liquid, this is the profile, I mean, this is the director field in some sense. Okay, so there's a first step that has to do with the fact that the material is prepared in the swollen state, and then when you take it out of the preparation stage, it deswells. And since the material is nematic, swelling is not isotropic, and this already has an effect. So as you will see, the thing curls up because of the drying process, and this has to do with the fact that the swelling is anisotropic. Let me not discuss this too much, but let me just discuss this step here. Now you have a curled material, nematic, cross-linked, and now you increase the temperature. So what you're doing now is that you're inducing the reverse, I mean the shortening along the director because you're increasing the temperature. And this is modulated spatially because here you shorten along the tangential direction. Here you shorten along the perpendicular, sorry, the other way around. So if you heat this, the material is long along the vertical and short along this. So if you heat it, it will become longer along the horizontal and shorter along the vertical on the bottom edge. The opposite on the top edge. So this is a bimetal strip in a sense, right? But obtained by texturing a nematic profile inside the material and then exploiting the phase transformation. Very well. So this can be modeled exactly with the, so this is the real experiment, and these are the simulations based on the energy I showed you before. So you can reproduce this. You can tune the material parameters so that, for example, you can predict the temperature at which the curvature becomes 0. So you started from something that was curved, you induce the opposite curvature, and you can ask yourself, at which temperature will the thing be exactly flat? You can answer. You do calculation, and you can answer. So what is behind this? So this is what we are asking. So this is, we're trying to minimize this. And so what is the type of problems that I am thinking about? So one is the direct problem. So in some sense, somebody has done the experiment for you. So it has prescribed the N0. So the nematic pattern has been put into the material. And you want to know what is the shape that results from this out of minimizing this energy. So you want to look for the U whose symmetrized gradient plugged into this formula minimizes the energy. And so this is the direct problem. There's a more interesting twist, which is, if you want, the engineer problem, so, which is the inverse one. So you prescribe a target shape, and now you want to find what is the director pattern that after energy minimization will lead to the target shape or to something as close as possible to the target shape. Of course, the second is much more difficult than the first. Inverse problems tend to be collection of infinitely many direct problems in some sense. So let's focus a little bit on the first. And I already showed you there is a brute force strategy. You place your problem in a computer and you look for the answer. Okay? So is there anything in between? I mean, is there anything conceptually more appealing, something, a way of asking conceptual questions about that? Well, one is to break the problem into two, or simply to look for a special class of problems, which are the ones for which the nematic, the deformation can be obtained at zero stress, so at zero energy. So you prescribe a pattern that can be realized by this equality. So by minimizing the integrand to 0. Okay? And so is it clear? So this is the datum of the problem. You compute this matrix field, and now you ask yourself, is there a U whose symmetrized gradient is exactly equal to that? Okay, this is a classical topic. I mean, there is a characterization for states that satisfy this. So here, this is a differential equation, of course. This is right-hand side, which is known. Differential operator on U, and you look for solution on U. And there's a compatibility condition that goes back to Saint-Venant. And so this can be done if this compatibility condition is possible. And so a nice program would be, let's classify the n zeros that lead to this. And once we have a toolbox of possible patterns that we can program into materials to accomplish interesting shapes. Of course, this may fail. And in fact, the example I showed you before with the bending of the strip with the pattern produced by the equilibrium solution of the liquid-liquid crystal, so through the anchoring conditions, that is not compatible. Okay? So the solution I showed you before is obtained with brute force. You're integrating numerically, so you're solving the Euler-Lagrange equation of the system numerically. Okay? And I don't know whether there is a more intelligent way of doing this, to approach this problem in this case. Let me move to the end. So this is a category of problems. Let me show you some further development that you can, on which you can build. So I've started from a theory that's very simple, linear elasticity, very simple energies, just the modulus of the different squares so we could see it. Now, two possible directions. One is that most of the things we see, and they are manufactured experimentally, are films. So quasi two-dimensional or even maybe quasi one-dimensional objects. And instead, I've always talked about a three-dimensional theory. So the natural question is reduced theory. Theories of reduced dimensionality, so plate theories, rod theories, shell theories, in which the effect of the director is built in. The other version is, so the other natural question is the nonlinear version of all I've talked about. So up to now, I was talking about linear kinematics, so I was always looking at linear strain computed out of displacement gradient. So U, the symmetric part of the gradient of that. Instead, you can do the same thing with nonlinear theory, in which the important quantity is the gradient of this function here. The nematic energies I was considering are all in the book by Warner and Terentiev. And in 2D, we have another very famous somehow system of equations that answers the question of whether there exists somehow, you prescribe something, is no longer some special strain, but will be some special thing associated with a gradient, which is this quantity here. It's one of the Cauchy strains. And what you're asking is whether you can solve something, you can find a map, Y, whose metric, so the question is whether you can prescribe a surface, you can prescribe the metric of a surface. And so the Saint-Venant system is replaced by another compatibility condition, this time nonlinear, which is the Gauss-Mainardi-Codazzi equations. And this is particularly interesting if you think of biological applications. So we had a nice talk at the end this morning about cells moving and swimmers moving. So I want to show you a nice application of this question in the context of biology. So the question is, I want to prescribe a mechanism through spontaneous deformations that achieves certain shape changes. Okay? And this is the very natural question that you ask yourself when you see a swimmer, a biological swimmer, a unicellular swimmer of the type we saw this morning towards the end. So what you typically do is that you look at, so this is some kind of alga, say, that is swimming. And what it's doing is changing shape while in a fluid. Because of the fact it's changing shape, it disturbs the fluid. The fluid reacts with propulsive forces. But at the root of this mechanism is the fact that this is a surface that is changing shape. How is it doing it? And if you look at this system here, I don't know whether you can see it. Can you see these stripes? So there are some stripes here, and here you'll see them, they are almost vertical, and here you see that they're most flat. these are high magnification images of this object. Before I was showing optical images in which these things are not visible. And so the question is, how does this organism produce the shape change? And since there are these little stripes, one possible mechanism is the following. The stripes slide one against each other. And by the shearing of this stripe, you produce this shape change mechanism. So this is exactly the same question I was asking before, except that it's not for a nematic elastomer, because as mechanism for spontaneous deformation, I'm not using the fact that certain fibers in the surface become longer or shorter. This is possible. There are studies for this. This mechanism is slightly different. So the mechanism produced by these sliding pellicles is that the spontaneous distortion is not an elongation along fiber, but is a spontaneous shear. So this is what you would be able to do with a smectic C elastomer. So if you have a material that can spontaneously develop shearing deformation, and you do this on a surface, and you can modulate this on a surface, you get a mechanism like this. And this can produce shape changes. And so this is the way this organism could behave if placed in a fluid. And then, if you integrate, if you couple the shape evolution of the object with the equation of motion of the fluid outside through the non-slip condition. So this is what would happen. And in some sense, what I'm trying to say is that this is a mechanism that in principle you could reproduce artificially if you were able to produce a smectic C material with a localized shear along the bands that you see here. So this is the mechanism that is being proposed. There is a localized shear, and this is a wave. So this is the position, and this is time. So there's a wave of localized shear that propagates through the body. Where the shear is large, the material forms a bulge. Where the shear is small, so what I'm saying is that the shear produces the fact that the strips become are no longer vertical, but they become sub-horizontal if you want, and the radius becomes large. So this is a mechanism for producing a traveling bulge in a material through localized shears on the surface. Okay. I think this is sort of representative of the type of things I'm interested in. So if you want, if you have suggestions or questions, I'm here.
Antonio, I'm a little confused about what your reference state is.
Yes.
So normally you define the strain relative to some state.
Yes.
And so, if you take one of these cells and you impose boundary conditions so that the director does that or something, then so are you saying that the reference state is the state before you've cross-linked for the strain, or what? Because you could imagine having a state.
Usually, the thought experiment I do is you imagine to heat up the sample. So it would be the stress-free configuration for the high temperature phase. Okay, so, as a general answer.
But you've sort of locked in the director when you cross-link in a situation with an inhomogeneous form. So you won't completely melt the
No. That's true. That's true. This will be there.
So you should have a reference state in which the strain is zero.
I should have?
And a reference state in which the strain is zero. In other words, I take some state and it's
so the case in which the strain is zero, in all the things I don't know whether I'm missing something, but in all the things I said, the strain equals zero means you are in the stress-free configuration of the high temperature phase. I don't know whether...
And U is defined with respect to
with respect to that.
with respect to that.
Yeah. So it's not the beginning of the experiment, it's not...
But it could be that your high temperature phase is actually distorted in shape.
Yes.
Okay.
It could be.
Okay. So zero strain means you have a state of things. Yeah.
You mean that the director is defined also in the high
No. No. The director is in in the low temperature. N lives only, if you want, in the
But I thought that and not red was the director in the reference.
Yes, because it's a fiber. So, I mean, these are subtleties, of course, but we
The
can...
reference configuration is the high state temperature configuration, then N is not defined there.
No, because in some sense, okay, this would work in... what I'm saying is that that model is natural in the case in which there is a procedure like the Finkelman one for which, there is a non-zero, there is a, how should I say that? There is memory of a special state which is imprinted. Yeah. So maybe I should think more closely about what you're saying, but yeah. Now the director lives in the. Actually, we'll have chance tomorrow to talk about this because I will speak precisely about these issues. But
I'll be there.
yeah, the director is in the current configuration.
Do we still have time, John, or we're
Yeah, go on.
seriously behind?
Wait, I could just pass if you want.
No, I don't want to suggest.
Nobody will be harmed.
I'm worried about the case of the glass. That is it possible that the director convects with the deformation?
Yes. So in the nonlinear kinematics version, this is certainly what happens. So you define a certain material fiber and then you convect it.
Yes.
Now this is a bit dodgy because it's a linear strain.
Oh, okay. No, that's
Okay.
fine. No, that's fine. Yeah. No, I'm fine.
No?
I think